Very well. Hello and welcome to today's lecture. So far we're done with chapter 1. We're done with chapter 2. We're going to start chapter 3. Chapter 4 and 5 are related to chapter 3. In chapter 3, we're just going to go over a little bit of introduction about probabilities. The actual work is in chapter 4 and chapter 5. Very well. So, Mat 10. Chapter 3, 3.1, page 1. Very well. So, what are the objectives and goals of today's lecture? So, in today's lecture, our goal or objective are as follows. First of all, we're going to learn about a sample space. Sample space. 2, we're going to learn about an event. What an event is. We're going to talk about simple probabilities. How to calculate some simple probabilities. Again, in chapter 4, in chapter 5, we're going to discuss probabilities of different types of variables in detail. But let us introduce the probability as a function first. Very well. Before going over the official definitions, think about this example. Suppose you have a coin and you want to flip the coin. Suppose you have a coin, a fair coin, it's not tilted, it's just a nice coin. And you want to flip the coin once, just one time flipping. What are the results or outcomes of this experiment? What are the results? You're flipping a coin. What do you get?
A 50-50 chance it'll land on one or the other side.
Very good. That's actually answering the probability. But what are the results? You either get...
Oh, a head.
Very good. Nice. Thank you so much. You either get a tail or you have a chance to get a head. How many results?
2.
2 results or 2 outcomes. So, in statistics, the collection of all possible outcomes, the collection of all possible results is called a sample space. So, the sample space of this experiment has 2 outcomes. We're going to write it in curly brackets, denoting we have a collection or set. So officially, we say that definition of sample space. In a probability experiment, so we are experimenting. In a probability experiment, the collection of all possible results the collection of all possible results or outcomes is called a sample space. A sample space. We usually denote a sample space by S. We denote a sample space by S. So in this experiment, we have two possible results, having tail or having head. You write S, or the sample space, equals to the set of, the collection of. Remember to use curly brackets, and we list all possible results to separate them by comma. So sample space denoted by S. So S is equal to the collection, the set of all possible outcomes. Very well.
I have a question about the sample space and
next, we're going to learn about an event. What is an event? Event is actually a sub-collection or subset of a sample space. So, definition of an event. An event is a sub-collection or subset of a sample space. We usually denote events by either capital letters E, F, A, V, or sometimes we use indices. We denote an event by, you either list these capital letters E, comma, F, the rest, or you can use indices. E sub 1, E sub 2, E sub 3, and so on. E sub 1, comma, E sub 2, comma, E sub 3, comma, the rest of them. Well, I expect you to ask, hey, in previous example, flipping a coin, the sample space is a set including tail or head. What are the events in that sample space? In the example on the right, events can be, guys, note that since an event is a subset or sub-collection of the sample space, we have to use curly brackets for them. So, E, event E, can be having just tail. So, you have a coin and you flip it once. You might have a tail. The second event or another event can be having the head. We have two events here. Any questions so far?
I have question is how many outcomes on the sample space? It look like what is the sample space, and they have two, so outcome is two, right?
Very good. 2 outcomes. Excellent. Excellent. Very well. Well done. Well done. Excellent, Felisa. Thank you so much. Let us move on to page 2. Before writing the rule, the principle, fundamental rule of counting, I'm going to ask you a question. Here's a question for you. Suppose I went to the store and I purchased 2 t-shirts. I went to the store and I purchased 2 t-shirts and I purchased 3 pairs of jeans. How many ways I can wear them? How many outfits I have? So how do you match these? 2 t-shirts with 3 pairs of jeans. What do you think?
6.
6. Very well. So first t-shirt, t-shirt 1. For the first t-shirt, I have 3 options for my jeans. First, pairs of jeans, or I can wear the second pairs of jeans. Second pairs of jeans, or I have 3 of them. I would like the third one. The third pairs of jeans. I have 2 t-shirts. For the second t-shirt, I have 3 options as well. So, t-shirt number 2, pairs of jeans, the first pairs of jeans, or I can wear them with second pairs of jeans. Suppose they have different colors. They were on sale, so I didn't pay that much. Second pairs of jeans. And the third pairs of jeans. So as you can see, if you count them, 1, 2, 3, 4, 5, and 6 different outfits. I have 6. 2 times 3, 2 times 3 actually gives me 6 options. So this is actually called the fundamental counting principle. The fundamental counting principle.
Professor,
Go ahead. So, what does it tell us? It tells us if a task includes 2 subtasks and the first subtask can be done in m different ways. ways, m different ways, and the second subtask, result genes, and the second subtask can be done in m different ways. So m and n different ways. Then the task itself can be done by m times n ways. M times n ways. This is called the fundamental counting principle. Like, I have 2 t-shirts, I have 2 options for wearing the t-shirts, I have 3 pairs of jeans, I have 3 options to wear my jeans. In total, I have 2 times 3, which is 6 different ways to wear them all. Very well. So I expect you to ask, here you're just saying that 2 subtasks. What if I have 3 subtasks? What if I have to choose between 3 different options, 4 different options, 5 different options? For example, let me give you some examples to clarify what I'm asking here. Example. Suppose you want to buy a car you have the following options. First of all, you have 3 different manufacturers. 3 of them. The first manufacturer is Ford, the second one is General Motors, and the other one is Honda. Okay, you're interested in purchasing either a Ford or GM or Honda. This is for manufacturer. Then you have the options for car size, the size of the car. Car size. You're not sure if you want to purchase a compact or mid-size car. So 2 options, compact or mid-size. And finally, you are in between different colors. You're interested in either having a white or red, or you're interested in black or green colors. So white color, red, black, or green. Well, how many options do you have? Here you have a task of buying a car, and it has 3 subtasks. Each subtask has its own options. How many options are available for you? In how many ways you can actually buy a car? What do you think?
Would it be 9 ways?
9 ways. So what's the fundamental counting principle?
24.
24. Okay. Note that we can generalize. Generalize. The fundamental counting principle. What do I mean by that? Here you have a task. So this is your task. The task can be done using some subtasks. Subtask 1, subtask 2. Now I'm adding subtask 3, which is the color of the car. Subtask 3. So the first subtask can be done in m ways. M ways. The second subtask can be done in n ways. And suppose the last subtask can be done in l ways. So in total, the task itself can be done by m times n times l ways. So what would be your answer here?
24.
3 times 2 times 4, 24 different options you have for buying a car. So we can also form a tree to actually connect these together and visualize it better. So I'm answering this example. We can also form a tree, decision tree. So this is a very basic concept that we are going over here. The more advanced idea using the decision tree are in social media. How when you are in a member of social media like Facebook, Instagram, and so on, how they use algorithms to connect you to your friends. Those are actually using complex decision tree algorithms. So this is the fundamental and basic idea of the decision tree. So here, suppose you have 3 different cars, Ford, GM, and Honda. Ford can be matched to a compact or mid-size car. So it can be compact, or let me write C, and mid-size. GM has these options as well, compact or mid-size. You have the same for Honda, compact or mid-size. For each of these sizes, you have 4 different options of color. So it can be white, or it can be red, or it can be black, or it can be green. You have the same 4 options for the mid-size Ford. So here you have white, red, black, and green. The colors. The same for GM. White, red, black, green, white, red, black, green. And for C, for compact size, Honda compact size, you have white, black, green, and red. And you have the same for the mid-size. Of course, Honda has mid-size cars, and all of them are coming in different colors. So the black one, the white one, the red one, and the green. So how many? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So either using the algebra and using the fundamental counting principle, or just using a decision tree to visualize our decisions here. So in this checkpoint, we're going to add a Toyota and a tan car. So let's take a look at this. We're adding a Toyota, so I'm going to use a different color. And a tan color. How many options do you have now? In how many different ways you can actually purchase a car? Now I'm adding a new brand, Toyota, with a new color, which is tan. How many options? Very good. 4 times 2 times 5 of them. 4 times 2 times 5. 40 different options. Very well. Another example for you. So the question on page 3 says, very well, you want to create an access code. We want to create an access code. It must be a 4-digit access code. Answer the following. First of all, if each digit can be a number between, so let me write it here. If each digit can be a number between 0 and 9, between 0 and 9, inclusive, it means that 0 and 9 can be included. First of all, how many access codes are possible? B, how many access codes are possible if you cannot repeat the digits? Very well. How many access codes are possible? How many access codes are possible if you cannot repeat a digit? It means that if you select the first digit, you cannot have the same digit in other places. 9 to the power 4. So here you have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Guys, 0 is included. 0 is included. You have 10 options. So here you have a task with 4 subtasks. You have 4 subtasks. The first subtask can be done in 10 different ways. This guy can be 0, can be 1, can be 2, can be 3, can be 4, can be 5, 6, 7, 8, 9. So you have 10 choices for the first subtask. Since you can repeat these, you have 10 choices for the second task. You have 10 choices for the third task. You also have 10 choices for the last task. So how many? 10,000. Excellent. This is equal to 10,000 different access codes are possible. 10,000. How about part B? You cannot repeat these numbers. Again, you have a task with 4 subtasks. The first one, the second one, the third one, and the last one. Okay, here we go. For the first one, how many options do you have? 10. What about the second one? You cannot repeat the digit. It means that if you take, for example, 0 as the first digit, you cannot repeat 0 again. So you're left with 9. Excellent. Then
And then
8. Excellent. Then
7.
excellent. Excellent. So how many?
5,000.
Very good. 5,000 and
40.
40. Excellent. 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 So if you can repeat those digits, it's going to be 10,000 different options. And if you cannot repeat those digits, repetition is not allowed. You have 5,040 different access codes.
I have question is B and why?
Now we're going to actually introduce the probability. On page 4, I'm going to write down the probability here. Page 4, probability. This is actually the classical probability. Why do you call it classical probability? Because in reality, we are working with more complicated functions. Well, let S be a sample space. Remember, a sample space is a collection of all possible outcomes. All possible results or outcomes. I'm going to take a sub-collection or subset of my sample space. Let E be an event. A portion, a sub-collection, a subset of your sample space. Then the probability of event A, the probability of event E is, they write it as P of event E, which is equal to, you have to do a little bit of algebra. It's going to be a fraction. On the numerator of the fraction, you have to write the size of your event, size of E, which is N of E. On the denominator, you have to write the size of sample space, size of S, which is N of S. This is the definition of probability of event E. Probability of event E. P is probability. event Remember, in flipping a coin, remember, in flipping a coin, the sample space was the set, including tail or head, and n of s, the size of sample space was just 2. You have different events. For event E equals to just having tail, the size of this event is equal to 1. So the probability of event E, which is n of E 1 divided by n of S 2, a half, or 0.5, or 50%. There is 50% chance of having a tail. There is a 50% chance of having tail. Well, welcome back everyone. So I'm going to stick to this example. Now, what if I ask you to find the probability of a different event? Like, I'm defining a new event. Let's see, suppose I'm defining event F to be just head. What is the probability of F? So this is the probability to have tail. Now I'm just giving you different events. Go ahead. What is the probability of you flipping a fair coin once you get head? How do you calculate that? Well,
50%?
50%, excellent. So the probability of F, event F, is equal to the size of that event. This event has only one member, so the size is 1 divided by, guys, remember that on the denominator you have the size of your sample space, which in this case is equal to 2, 1, 2. So here you have 2. 1 divided by 2 is 50%. 50%. There you go. Excellent. So let's take a look at a simulator. Just want to share this simulator with you. This is the link for the simulator for those of you who want to actually run this simulator. Here we go. So let's go to this applet. So this is an online simulator for flipping a coin, and the event is head. So take a look at this. It's head. So your event is having a head. So what are we going to do? We're going to flip the coin once, one flip. So let's do that. What is the probability of head? Let us flip it one more time. Flip it one more time. We can continue this process. We can flip it 5 flips. Very well. Do you see that? Do you see the oscillation between these points? I'm going to flip it 1,000 times. And these are all the probabilities or proportions that I'm getting. As you can see, it's getting closer and closer to 50%. 0.49, 1353, which is close to 50%. So you can repeat this as many times as you want, and there are online simulators calculating the probabilities for you. In chapter 4 and chapter 5, we're going to use our calculator to calculate probabilities for us. On page 4, we have an example. A company is conducting a phone survey of randomly selected individuals to determine the ages of social networking site users. So far, 975 social networking site users have been surveyed. So in total, you have 975. As you can see, the total numbers in your collection is 975. It means that there are 975 people who took the survey. The frequency distribution at right shows the results. Question says, what is the probability that the next user surveyed is 23 to 35 years old? Well, take a look at your distribution here. On the left-hand side, on the left column, you have ages 18 to 22 with frequency 156. 23 to 35, the frequency is 312 people. 36 to 49, you have 254 people who took the survey. 50 to 65, you have 195 people. And 65 and over, you actually have 58 people. Question says, what is the probability? What is the probability that the next user surveyed is 23 to 35? You're finding the probability. You need to form your fraction, 23 to 35. Let us write the question here. Question says, hey, you have the following table. You have some categories, you have some events, ages, and the frequency or the size of each category. Frequency or the size of each category. Each category. Okay, the first category, ages 18 to 22. The frequency is 156. The second category, 23 to 35. Okay, if this category has a size 312. Next category, 36 to 49. This category has size equals to 254. And then 50 to 65. You have the category size 195, and over 65, the category size is 58. Perfect. And the total sum is equal to the sum of all frequencies, 975. Question says, what is the probability of the event, what event, that person lands in the category ages 23 to 35. The person is 23 to 35 years old. This is your event, of course. This is an event. Remember that. To form the probability, what do we need? We need the size of that event. divided by of the size of your sample space. Your sample space includes all people who took the survey. How many people? So sample space is equal to the set of all people who took the survey. So what is N of S? What is N of sample space? How many? 975 people. 975 goes on the denominator. What about your numerator? What is your event? Event, the person is 23 to 35 years old. But what's the size of that event? 23 to 35, which is 312. You do the division, you get a decimal, 0.32. You convert that into percent, which is 32%. This is the probability. Probability must be between 0 and 1. What's the meaning of that? It means that we do not have negative probability. The probability is negative 12%. It's wrong. Negative 20% is wrong. So let me use a different color. If somebody says, hey, the probability is 150%, wrong. 150% probability, wrong. We don't have probability 150%. These are wrong values. Probability can be 0, any number between 0 and 1, and also 1. So we are happy here. Otherwise, give a sad face, it is wrong, absolutely wrong. Very well. So answer me this. Page 5. Answer me this. I have a question for you. Suppose we roll a die once. So our sample space, you know, that includes 1, 2, 3, 4, 5, and 6. Here's my question. Find the probability of having 7. How do you calculate that probability? What's the probability of having 7? What do you think? 0, very good, excellent, very well. The probability of having 7, it is 0, very good. That probability is equal to 0, nice. Since having 7 is impossible, its probability is equal to 0. So if you ever wonder when the probability can be 0, if you have impossible event like having 7 in this sample space, the sample space doesn't include 7. It's an example of probability equal to 0. Excellent. Thank you for your participation. Excellent, Myra, Elaine, Emily, Sammy, Shauna, Vanessa, Juan, Nan. Excellent. Excellent. Very good, Felissa. Yes, there is something wrong. We don't have 7. So you're working with just normal dice. Very well. Excellent, everyone. Thank you for your participation. Thank you. So another question for you. Suppose I ask you to find the probability of the following events. Find the probability of having an odd number. Also, I ask you to find the probability of having an even number. So having an odd number, it can be 1, it can be 3, or it can be 5. An even number, it can be 2, it can be 4, or it can be 6 itself. So how do we calculate these probabilities? What do you think, guys? Suppose this is the probability of event A, event E, which says even numbers. Let's write odd for E, odd numbers, or let's write numbers. So the probability of event O is how many odd numbers? 1,
3.
3, and 5, which is 3. 3 divided by
6.
6, which is a half, or 50%. The probability of having an even number. So let's call it event O. Even numbers. How many even numbers? 2, 4, and 6. Again, 3. Excellent. 3 divided by 6, which is a half, or 50%. So note that if I add 50% and 50%, 50% plus 50%, I get 100%, or 100 divided by 100, which is 1.
And I have a question. And what is the odd number and even number?
Very good. So the complement of event E is denoted by E prime. The probability of the complement of an event is 100% minus the probability of event B. So you can say that here in this example, it says, what is the probability of having a number that is not even? So the probability of not even, it's not even, equals to 1 minus the probability of having an even number. Not even, so think about odd, but for now, just not even. So this is 1 minus the probability of having an even number. How many even numbers do you have? 2, 3, and 4. 3 numbers. 3 divided by what's the cardinality or size of the sample space is equals to 6. So you get 1 minus a half, which is a half, or 50%.